In this video, we are continuing our look at carboxylic acid derivatives, focusing on physical and spectroscopic properties. Let's consider the physical properties of a few examples of carboxylic acid derivatives. So in the first column, we're comparing an alkane with an ester and an alcohol. And because we are talking about dispersion forces compared to dipole-dipole interactions, compared to hydrogen bonding, we need to make sure we are comparing similar size. So this is 72 grams per mole, 74, and 74 grams per mole. And the boiling point, this is 28 degrees, 57, and 99. So no surprises. Here we have dipole-dipole interactions when it comes to an ester, and so these are stronger than dispersion forces, but not as strong as hydrogen bonding. In the center column, we have another series of compounds to compare, and so our alkene weighs 56 grams per mole, our ketone is 58, and then our alcohol is 60, and our amide is 59. So again, we're talking about dispersion forces and dipole, hydrogen bonding, and more hydrogen bonding. So our boiling points are -7 degrees Celsius, and then 56, 82, and 221. So the hydrogen bonding is incredibly important. Strong intermolecular forces, so it takes a lot of energy to break apart those intermolecular forces. In the last column, we're looking at amides, but here it's a primary amide, so we've got more hydrogen bonding possible. Here, this is a secondary amide. The nitrogen is connected to two carbons, so only one hydrogen available for hydrogen bonding. And then here in this amide, there's no hydrogen bonding possible. So we are kind of breaking the rules because we are looking at different sized compounds. So this is the molecular weight. But when we look at the boiling point, we said 221. This one, even though it's bigger, it has an extra methyl group, it has a lower boiling point. And this one, at the highest molecular weight, has the lowest boiling point. And so the number of hydrogen bonds makes a big impact on the strength of the intermolecular forces. Next, let's consider the spectroscopic properties of some carboxylic acid derivatives. For IR, I want you to focus on 1700 inverse centimeters for the carbonyl. Keep in mind, some tables of IR frequencies will give you a kind of a distinction between what's the range for amides and what's the range for acids and what's the range for esters. But many of those overlap with each other, so I recommend focus on 1700 and then use other information to figure out whether that carbonyl belongs to an aldehyde or a ketone or an acid or an ester, etc. Here we can see the range. We have some lower frequencies for the carbonyl absorption when it comes to amides, and then a little bit higher for ketones and for acids, and anhydrides can be significantly higher than the typical range. But there's nothing else that really absorbs there, and so it'll be something that would stand out. It might not jump out at you as a carbonyl, but it would probably stand out as a significant peak, and then you can look at a table to find out what it is. For proton NMR, if you have a hydrogen connected to a carbon that is connected to a carbonyl, whether this carbonyl is part of an acid or an amide or an ester, these are going to show up around 2 to 3 ppm. And then for C13 NMR, I like to think about 200 ppm for any carbonyl. Carbonyls definitely absorb at the highest range, higher than alkenes and aromatics. 200 ppm is probably too broad of an estimate. notice when we are talking about aldehydes and ketones, they do absorb around 200 ppm. When we have different carboxylic acid derivatives, these are closer to 170 to 180, so just be aware of that. Let's see if we can figure out the structure of the compound that gave these spectra. What should jump out is a carbonyl around 1700. This is a little bit higher than 1700, so that might give us some information, but this gives us more information. This is also very strong. It's about 1200 inverse centimeters. That is a carbon-oxygen single bond, so it's quite possible that we are talking about an ester. Here we have sp3 hybridized CHs, and that's probably about it. Looking at the proton NMR, let's call this signal A, B, C, and D. And I forgot to give you the integration. This is 2 to 3 to 2 to 3. So the first signal at about 4 ppm, this would be consistent with, it integrates at 2, so it's a CH2 group, and it absorbs at 4 because it's probably next to an oxygen. It could be next to a halogen, but we know from IR that we have an oxygen, so let's go with this guess. And then it's splitting, it is a triplet, so that means it must have 2 neighbors. So this is a signal that corresponds to A. Looking at signal B, this integrates to 3, so this is a CH3 group, and it absorbs just over 2 ppm, so that's consistent with a carbonyl. C integrates to 2 hydrogens, so that would be a CH2 group, and it has lots of neighbors, nothing especially electron withdrawing. And then finally D is a CH3 group, and we know that has 2 neighbors because it is a triplet. So let's start here. We have a CH3 connected to a carbonyl. From this we can guess that the carbonyl is part of an ester, and so that oxygen is next to a CH2, next to another CH2, next to a CH3. So this would be signal A, B, C, and D. A, you would expect to absorb between 3 and 4. It does, and it has 2 neighbors, so you would expect a triplet, and that's what we have. B, you would expect it to absorb around 2 to 3, and it does, and you would expect it to be a singlet because it has no hydrogen neighbors, and it is. C has 5 neighbors, so we would expect a sextet. It's kind of hard to tell, but we can see a lot of peaks, so obviously a lot of neighbors, so this is consistent. And then finally D, this should be pretty normal, so close to 1 ppm, and it has 2 neighbors, so we would expect a triplet, and that's what we have here. So this compound is propyl acetate. Here's a new compound, and this time we have IR, proton NMR, and C13 NMR. So from IR, we have a carbonyl around 1700. This one is a little bit lower, so it could be maybe an amide, maybe a carboxylic acid. But we don't have any evidence of a carboxylic acid, so maybe this is an amide, but I'm not sure. Here, 3000, so we have some sp3 CHs, and up above we have some sp2 CHs. We have sharp peaks at 1500 and 1600, so we probably have a benzene, and this signal is pretty strong. Possibly be a CO single bond, though that's a little bit higher than usual. Well, there's a chance that this is an amide, and so if that's the case, this could be a CN bond. We've got some possibilities. Next, let's look at the proton NMR. So signal A integrates to a total of 5 hydrogens, B integrates to 2 hydrogens, C integrates to 3, and D also integrates to 3. So here we have a set of hydrogens just above 7 ppm. So this is consistent with an aromatic ring. Because it integrates to 5 hydrogens, there must be 5 hydrogens on the ring, which means one other substituent. B absorbs at 3.7-ish, so that is pretty high. It could be a hydrogen on a carbon that is next to something very electron withdrawing. It is actually a CH2 group because it integrates to 2 hydrogens, and it is a quartet, which means it has 3 hydrogens next to it. Looking at signal C, this is just below 2 ppm, and this integrates to 3 hydrogens, so this is probably a methyl group next to a carbonyl. And then finally D, this is another methyl group, but this one is next to a CH2 group because it is a triplet. Next, when we look at the C13 NMR, this could be our carbonyl signal, and then there's actually 3 separate signals here, which means we have 4 signals in the aromatic region. So from proton NMR, we know that we have 1 substituent, and so we would expect to get 1 signal, and then a second signal, a third signal, and a 4th aromatic signal, so that makes sense. And then down here we have some sp3 hybridized carbons. So what have we got? If we have a CH3 next to a C double bond O, it is next to something, and then we also have an aromatic ring that's next to something. And then what are we missing? B and D, we have a CH2 connected to a CH3, and that is connected to something. Now, if this was a halogen, then we would be done with our molecule, so that doesn't work. If this was an oxygen, then we could only have 1 more bond, so we can't connect both the aromatic group and the ethyl group if that is an oxygen. So what if it is a nitrogen? With a nitrogen, we can have 2 more bonds. So one of these could be the aromatic, and the other one could be the ethyl group, CH2, CH3. So is this consistent with IR? We have sp2CHs, sp3CHs, we have a carbonyl that could be part of an amide, and then we have some CN bonds as well. By proton NMR, the aromatic ring would correspond to signal A. So keep in mind, these are not equivalent to these, which is different from this, but those hydrogens are all similar to each other and they're kind of overlapped and we can't really see what's going on. So they are separate signals, but we've just lumped those signals together and counted a total integration of 5. This one would be B because it's a CH2 group with 3 neighbors, and so this is D. This one would be B because it is a CH2 group with 3 neighbors, and then this would be D because it's a CH3 group with 2 neighbors, and then this one would be C because it's a CH3 group with no neighbors and next to a carbonyl. So let's focus on this CH2 group. So a hydrogen on a carbon connected to a nitrogen, that's usually not as high as what we have for an oxygen, but because this nitrogen is also next to a carbonyl and also next to the benzene, all of these things could be increasing the electron withdrawing nature of the nitrogen, which means that there's more deshielding, which pulls these hydrogens to a slightly higher ppm. And then finally, thinking about the C13 NMR, we have our carbonyl, we have our aromatic hydrogens, And then we have 1, 2, 3 sp3 hybridized carbons. Now make sure you keep getting lots of practice interpreting spectra.